So we've got the first example from the second lecture regarding strain. And here we're given that we have a rigid beam ABC. So a rigid beam means that it's free to rotate, but it can't deflect relative to itself. It can't bend, essentially. So we have a pin at A. C is supported by a wire CE. B is supported by a wire BD. Because this beam is rigid, it's free to rotate. These wires will deflect, and point C will deflect, but this won't bend. It'll stay straight the entire time. Wires BD and CE are shown to have different lengths. Also, the distance from the pin to point B and to point C, we have some different lengths here as well too. We're shown that there's a load being applied to this rigid beam. We're not given the magnitude. The only information that we're given is the deflection of point C as 10 millimeters. We don't need to know the load because all that we're doing is quantifying strain. All that we really care about are deflections, relative deflections at this point. So this question is asking us to find the normal strain, the average normal strain in wire CE, which is the longer wire out here at the end, and then wire BD. So I've set this up, given required. Our solution is where we're going to start right now. And so just like you see in the required section, I've split it up into two different subparts to help guide the reviewer. Here we have part A is for wire CE. And so I'll mimic that. I'll have the same heading over here in my solution section. So here we'll have section or a subheading for A, and we'll be solving first for the average normal strain in wire CE. Okay, so wire CE is relatively straightforward. We can draw a diagram of what the deflection is going to look like because we know it's also often helpful to write down the fundamental equation that informs the rest of our problem. So here we know that normal strain is equal to the final length minus the original length divided by the original length. So now we know everything that we need to solve for to get this average normal strain. We need to know the original length, L naught. We need to know the final length, LF. Here, L naught is easy. L naught we're already given as 2 meters, so that's going to be in our denominator and here in our numerator. The final length, or we could write this as the change in length at the top. And it's nice for point C because we know that it rotates down. Let's go ahead and draw a figure really quick to illustrate this. So our original orientation is horizontal. Here at point A, the beam is going to rotate but not bend. And we know that the overall deflection at point C, the change in length of wire CE, is 10 millimeters, or the same thing as 0.010 meters. So this is our change in length. This is our final length minus our original length. And so this numerator is really just the same thing as saying what is the change in length, or delta L divided by L naught. So for point C, for wire CE, this is very straightforward. I can simply plug in the values that I have. Normal strain for wire CE. The change in length, the numerator, is just this 10 millimeters. 0.010 meters. The original length is 2 meters. And so we get the normal strain. This is simply 0.005. And even though it's a dimensionless quantity, we always give it in units of distance per distance, just to make it clear that we're talking about a strain. And so in this case, we could say meters per meter. You could also say millimeters per millimeter. It would be the same thing. Okay, so this is our final answer. We'd bring this over to the right-hand side, and we say that the average normal strain in wire CE is equal to 0.005 meters per meter. And again, in terms of sign convention, this is going to be a positive quantity because wire CE is getting longer. We have a positive normal strain. It's in tension. It's elongating. So this would be a positive value. So now, the slightly more complex part is subpart B, where it's asking us to find the average normal strain in wire BD. So it's the same exact initial equation. The average normal strain is equal to the change in length over the original length. We have the original length of wire BD, that's 1.5 meters. That's given to us straight from the diagram. The trickier thing is going to be, well, what is the deflection? What is the change in length of wire BD? And so if we use the same type of diagram right here that we used for CE, my beam starts out horizontal. It's rigid, so it rotates, but it stays straight. And we know that the deflection here at point C is 0.10 meters. At A, it doesn't deflect at all because there's a pin. All right, so we know deflection at C, we know deflection at A, but we really want to figure out the deflection at point B right here. This is our question. What is delta BD? And because this is a rigid beam, this diagram creates a triangle, so we can simply use similar triangles to figure it out. You could figure out the slope of this line, multiply it by this length. It would be helpful to write down these lengths right here. So the overall width of our triangle is 5 meters. It's given from our diagram. The distance from A to B is given as 2 meters. And so using similar triangles, I can say that the ratio of this height to the overall length has to be the same as the ratio of this height to its length from A. So the ratio that I set up would be this height right here, which is 0.010 meters divided by its length, which is 5 meters, has to be equal to this unknown distance, this unknown displacement, delta BD, divided by its horizontal component from A to B, which is 2 meters. And we get that delta BD is equal to 4 millimeters, or 0.004 meters. Okay, so this is just the numerator portion of our strain. And so now I can calculate the normal strain, BD equals the change in length of BD over the original length. The change in length we calculated as 0.004. The original length is 2 meters, or, I'm sorry, 1.5 meters. And that gives us an average normal strain, still positive because it's elongation, of 0.00267 meters per meter. And I would put that over here. Average normal strain, wire BD of 0.00267 meters per meter.